Hello everyone, welcome back. Let's continue with the second part of the video. Those who haven't watched the first part, I would highly recommend doing so. The link of the first part you can find in the description below. Now, the third step. The next one we want to say about the temperature. What was our condition for temperature? If let's call it absolute, while first let me write T underscore target minus current temperature. So we want to take absolute value of the difference of these two. If the difference of these two is greater than whatever number you can say, we can call it 1 Kelvin, zero point 0.5 Kelvin. So it depends. If you say 1 Kelvin, we'll find out the temperature between 39 to 41, or you can say zero point 0.5. So let me put it 0 0.5. If the difference of absolute difference of these two is greater than 0 0.5 Kelvin, then it should change the flow rate. So let's call it M flow adjusted. So we are giving another name because we need to define how it should be like that. If it is less than 0 0.5, then it should give the M flow current. And this one is okay here. What we had M flow conditional. Let me make it little smaller. It is too large. So what is our M conditional? Our M conditional, it is checking another condition for the temperature. If it is greater than 0 0.5, it will adjust the flow rate. If it is not, then it will use this one. You can do one thing. You can put this entire statement at this place. In that case, this statement will be too long. It will work, but sometime it becomes difficult to find an error. That's why I'm doing it separately. But you can also do that. You can just copy and paste this one over here like that. So you can see there are a lot of things. So I don't do that. It makes life easier like that. Now, okay, now we have defined this. We have defined both of these conditions. Now we need to see how this flow rate should be adjusted. So how it should adjust? M flow adjusted, it should be equal to the M flow current plus M flow current time any factor. So we can define this factor, it is not that important. So what we are doing here? So we are saying the M flow adjusted. So how this flow should adjust? So it means it should take a current flow and not equal plus. It should take a current flow, and if these two conditions satisfy, if the iteration is equal to the multiple of 10 or the difference is greater than 0 0.5, then it should take the current flow rate and it should add some value in this current flow rate, which should change for the current flow rate by some factor. So that is our adjusted flow rate. Now we need to define this factor. This factor you can define in different ways, but the easiest way that I find, so that this factor should change according to the temperature. So if the difference is big, the factor should be bigger. If the difference is small, the factor should be smaller. So you can define in different ways. So there is one way how you can do that I have done over here. So it is something like that, a factor of 5. So here, so what I am doing, so it is taking a current temperature that we are getting through report definition in Fluent here, that we have defined current temperature over here, or the current temperature of the battery cell. So what is the factor? Current temperature minus target temperature. So it is checking how far this temperature is. So current minus target divided by target. So it is checking in term of percentage, or actually in term of fraction. So it is checking how far this current temperature is from the target temperature. So, and I'm just multiplying with another factor of 5 because that just give a reasonable change in the flow rate. So you can adjust this one. But the beauty of this factor is that for example here, if the current temperature is higher, so it means this factor would be positive. So that's what exactly we wanted to have. If the current temperature is higher, we want to increase the flow rate. So that's exactly what happened. So current minus target, this factor will be positive. So it means this entire expression will be positive and the flow rate will increase. Or other way around, if the current temperature is less, so our target is 40 and current temperature is 35, so it means it will be negative, or the system is extra cool down, so we want to reduce the flow rate, so it will automatically subtract from this one. So it means this factor works really well, so it can work in both ways, positive and negative. So you can do it separately or you can just simply write over here, so it's up to you. Now let's go back and let's copy this one. So we need to define our amp flow conditional. Let's go back. uh, so we need to define amp flow conditional. So let's say new, let's write our expression over here, and here we have amp flow underscore conditional, amp flow conditional. So if absolute T target minus T current, so we have taken absolute, so here the order doesn't matter. It is saying there is some error. So let me check what error do we have. Syntax error. T underscore target. So this one we already have. Okay, let's write from start. I don't know what is missing, but okay. Absolute T underscore target minus what we had defined, current temperature is okay, we need here and here one bracket greater than 0.5 Kelvin. Then we want to use amp flow adjusted, otherwise amp flow current. Yes, now we don't have any syntax error. Yes, this one should have been in the brackets. So now if target minus current is greater than 0.5, we should have amp flow adjusted, otherwise the current flow rate should be used. So let's say okay, again amp flow adjusted is not defined. Yes, that's fine. Okay, now we have to define last one, amp flow adjusted. Say okay. Now new, and here we want to define amp flow underscore adjusted, and here we have already defined, so not here, from here I can simply copy paste this one over here, target temperature, but T underscore target, and again here T underscore target. Okay, so now amp flow current, so current flow rate plus current flow rate into that factor, and we can say okay. Now you see we have defined everything, so now everything has been defined. So now what we need to do, just we need to set at the inlet amp flow in, that's where we had started. So let me pull that back. So amp flow in, so that was the amp flow underscore in, so that's how we had started. So it means it is the expression that we have to put it at the inlet. So let's go back and say let's go our inlet, edit, or just go over here mass flow rate. So I have already converted into the mass flow rate, and in drop down you can see all those mass flow rate, and here just select the correct one, amp flow in, because if you will select something else, so all these expression will not work. So just say amp flow in and apply, and okay. So again, it will go in this order. We have defined target flow rate, sorry, target temperature. We have defined initial flow rate, and we said, okay, our boundary condition is this one, m flow in. So what it will do, m flow in, it will go and check iteration is less than 10. So if when the iteration is less than 10, it will use initial flow rate, which is 2 gram per second. When it will be greater than 10, it will use m flow modified. What is m flow modified? That we have defined over here. M flow modified, for that we want to apply two conditions. One is for iteration, other one is for temperature. So let's do it one by one. If mode iteration 10 is equal to 0, so if the residual of this one is 0, it means this condition will be satisfied. If this condition satisfy, then it use m flow conditional. M flow conditional that we have defined in next step. If this condition doesn't satisfy, so it will use m flow current. M flow current is whatever flow rate was in the previous iteration, so that will continue. And this m flow current we have extracted through report definition. So now we have to define m flow conditional. M flow conditional is over here. So here we are defining m flow conditional, and here we need another condition because we wanted to have two conditions. One is for iteration, other one is for temperature. Now if absolute T target minus current temperature, so it will check the difference of these two, target minus current, and it will take the absolute. So absolute, so it means it will disregard this sign. So if the absolute difference is greater than 0.5, then it will change the flow rate. If it will be less than 0.5, so it will continue whatever the flow rate was in the previous iteration. So it depends, this number, it depends on your requirement. Now we need to define this m flow adjusted. So it is straightforward. M flow adjusted, it should be current flow rate plus current flow rate into some factor. This factor you can use hard factor, you can say, let's say 10%, 20%, 30%, but that's not a good idea, because let's say if you say 20%, it means the change will always be 20% regardless of the difference between these two. So we need some dynamic factor that could change accordingly as the difference between these two, and also this sign should also change, because if you use hard factor 20%, then it means if you also need to change the sign for uh, both condition if the temperature is higher or lower. So that's why we have copy this condition with this expression. So we say set current temperature minus target temperature divided by target temperature. Oh, we have defined our all of expression in the Fluent, and now we're ready to run our simulation. Right click. Okay, let's go to the run calculation. Here I have defined maximum iteration of 500, and you will see that the flow rate will change as the simulation will progress. Right click and run. It will take some time to run the simulation, so I will stop in between, or I will fast forward, and in between I will give some comments and see what is happening. A couple of iterations have already been finished. So here you can see the flow rate is changing after every 10th iteration. So after 10th iteration, flow rate has increased, after 20 further, and after 30 further. It is happening because of the temperature. So you can see initially in first 10 iteration, temperature went up to 45 degrees Celsius. So temperature was quite high. It has changed the flow rate, and we had seen after 10 iteration flow rate had increased. So after 10 iteration, it has reduced up to 44 degrees Celsius, and it is keep on decreasing. So it is going forward. So as soon as the simulation will finish, I will show you the end result. And one more thing in between I can show you. So here is the residual. It is behaving like a quasi-transit simulation. So you can see the residual is going down, and after 10th iteration, when the flow rate has changed, it has increased once again. So it is going up and down, up and down. Let's stop here and see the simulation results at the end of the run. The simulation has almost finished, and here you can see the flow rate had increased up to 6.5 gram per second, then it decreased once again. It happened because initially I had given the target temperature of 35 degrees Celsius and it was increasing. Then I changed it again to, and the current temperature went below 40. It was 39 or something. So I changed the target temperature to 40 degrees Celsius. So now the current temperature is increasing again and the flow rate is decreasing. Here the residual has almost uh, reached. So we have reached the end of the simulation and we have fully converged solution. And here is our temperature. So first, as I mentioned, it went below 40 degrees Celsius, almost 39, where I changed the target temperature to 40, and it increased once again up to 40 degree Celsius by increasing the flow rate. Now let's look at our end results. So I have plotted the temperature. Here you can see the temperature of these two battery cells, and we can see the temperature in report plot. So let's go to this report, and volume integral, volume average, we want to see the temperature. Let's okay, volume average temperature and compute. And here you can see the cell 2 temperature. Average temperature is 39.5. So I had used a temperature condition of 0 0.5 Kelvin. So it is in between 40 plus minus 0.5. So it is in between 39.5 to 40.5. So that's how you can use expression to manipulate the flow rate to achieve the required temperature. So that's it for today. In next video, we will look at our fourth example where we want to change the inlet flow rate based on the outlet temperature, and we will write the series of expression like that for that example number 4. If you like the content, don't forget to like and subscribe my channel. Thank you so much and see you in the next video.